Hi everyone, welcome back to this channel and I hope you guys are doing well. Today we are going to solve another LeetCode problem that is recover binary search tree. Okay, this is yet another one of the LeetCode famous problems. We can judge it at least based on the number of likes. Okay, so we are given the root of a binary search tree where the values of exactly two nodes of the tree was swapped by mistake, and we need to correct that swapped. We need to revert that back. Now, before jumping into the problem, let's quickly recap what a binary search tree is. Suppose we are given a node, let's say y, and it has its left subtree ls, let's say, and then right subtree it is rs. Okay, now let's say any node x that belong in the left subtree, and we have another node that is z which belongs to right subtree. Okay, now if it is a BST, then every node in the left subtree, that is x, must be less than y, y that is our current node, and every node in the right subtree must be greater than the current node. Okay, and this property holds true for each node in the binary search tree. And because of this property, if we perform in-order traversal on a BST, our node values will be in sorted order. Because what in-order traversal says, first explore in the left subtree, then process the current node, and then go to right subtree. So this is left subtree, process our current node, and go to right subtree. Okay, so because of this property, values we get from in-order traversal is sorted. Okay, let's now go back to our original problem. In the problem, we are not allowed to change any structure, but only swap back those two node values. Okay, so let's simulate these two examples. Let's perform a dry in-order traversal for this tree. We cannot say BST because it is not BST yet. So if our in-order will be 3, then 2, and then 1. So we can clearly say that the array is not sorted in increasing order. Okay, so one of the brute force approach that would come is that, okay, we can take all the values from the given tree and then sort them. After sorting the node values, we again perform in-order traversal on BST and check if the nodes and its corresponding values are matching or not. If it does not, then we'll just change the value on BST. So we'll start from here and then go to left, because in order traversal we go left, then process current node, and then go to right subtree. And for this node we do not have any left child, so we process this current node with this value. Is this matching? Not. So what we are going to do, we take this value and change to this one, for example 3 to 1. Okay, and move to our right subtree, and here our current pointer will go to the next right subtree. Is this matching? Yes, it's matching. Okay, so there is no left or right subtree. It will go back to here and then here again. For this node, our corresponding value will be here. Is this matching? No. So change the value 1 to 3. Okay, now our final BST will be 3, 1, and 2. So this will be our answer. So let's take another example. If we perform in-order traversal on this tree, we'll get, again, the traversal is not sorted, so we are going to sort it. Again, we are going to perform in-order traversal on the given tree, and we'll check if the corresponding sorted values with the node values matches or not. Okay, so we'll start from here. Obviously, because of the in-order traversal, is this value matches with this corresponding? Yes, it matches. So let's move to the next node. Is it matching with its corresponding? Whatever, this value has to be there, but it is not there. Okay, so we need to change this node value to 2. So let's do that. Give it 2 and move to the next node. Again, it's not matching, so we're going to change it from 2 to 3 and move to the next node. Now for this node, its corresponding value is matching with the node's value, so we are good to go. So our final BST will be, let's quickly implement this approach. So I'll just start first to get the values, node values in an array, and for that I'll just define a function, recursive function, in-order traversal. And then what we are going to need here is the current node and one vector to store the values, and of course we'll take it by reference. And if root is equal to null pointer, we need to return from here. Otherwise, first we'll explore the left subtree, and then process the current node. That is, we need to take the value, that is order, and then right, and then explore the right subtree. Right subtree. So I'll just call it that list array of values order, and then we'll invoke this function to traversal. We'll pass it the root node and then order. Okay, now we have array of those values. Now we'll sort it. I'll use the C++ STL's sort algorithms, and then this is order to begin and then end. Okay, again we'll perform in-order traversal on that tree, and we'll check if it corresponding value in the order array is matching or not. For that, what we're going to need is a pointer or that keeps track of the values in the order vector. And I'll just overload this function again, instead of naming different, that is void recover tree. For that, we're going to need this current node and then values, and then here we are going to need it by reference, because the values we have already processed in the order vector. We don't need to visit them again. Okay, again the same base case will be here also. If root is equal to null pointer, then just return back, don't need to go further, and then go to left subtree, that is this one, order, and our pointer will be same in this case. Okay, now whether it is equal or not, we can check that. If we can say root value is not equal to our corresponding, then we can assign it to order. Okay, and then go to right subtree. Then I, and of course we need to advance the power pointer. Okay, and we call this overloaded function again, because tree and then order and then I. Okay, so everything looks fine, so let's run it. Okay, so our sample test case are working fine, so let's submit it. Alright, now the time complexity for this implementation will be n log n, and that is only because of this sorting. Okay, but hey, if you go to the description of the problem, it is saying that exactly 2 nodes of the tree were swapped. Okay, so if we need to figure out those 2 nodes, we don't need to sort the entire array. Okay, let's examine. Now for an array, let's say we have an array A. If it is sorted, then I will always be greater than ai minus 1. Okay, for any I is greater than 0. Okay, now let's take an example of those swapped binary tree and examine this. How? If we perform in-order traversal on this tree, binary tree, then we'll have, okay, I'm just write down those values quickly. Now if you traverse this array, first time we will encounter that here it not satisfying the condition of sorting array. Okay, so this is bigger, this cannot be here. Okay, so let's for a moment let's give it a name x. Let's store in a variable x, and this one is y. Okay, we'll come back in a second why we are assigning this value to y. Okay, and then 12 is greater than 8. Okay, 16 is greater than 12. Okay, this satisfying the condition of sorting array. And then 24 is greater than 16. Okay, but here again 4 is not greater than 24. Okay, so this one is small, this cannot fit here. So we found x in the beginning, and let's assign it to y from here. Okay, now this will not satisfy, this condition won't satisfy in 2 places because the 2 nodes were swapped. But if 2 nodes were adjacent nodes, parent child relationship, then they will be in adjacent in our in-order traversal. So if that was the case, then this will be x and this will be y. But if they were not adjacent nodes, then at 2 places we will encounter this condition that is violated. Okay, for example here, so here since this one is smaller, it cannot fit here, so we'll assign it to y, and this one is bigger and it cannot fit here, so we'll assign it to x. Now we have x and y. Once we find this x and y, we'll traverse this array again, perform inner traversal, and we'll see if any of the nodes equals the value of x, we'll give the value of y, that is 4. In this case 32 will give the value of 4. Okay, again we'll keep going, and eventually we'll encounter a node that's value is 4, then we'll give the value of x, that is 32. Now our binary tree is a binary search tree. Okay, so we'll quickly implement this approach. We don't need to sort here, so I'll just remove this one. Okay, let's say we need to find identify the values x and y. Let's say initially we assign it to -1 or okay. And also we are going to need a boolean flag that is whether the x is found or not, because we are not going to assign it again. Okay, so let's say found x and then assign it to false in the beginning, and let's start traversing that array as equal to 1 and then less than size and I. Okay, if any case that order I is less than its previous value, this one. Okay, if not found x, then we'll assign that x we have found that is in previous positions. Okay, again I'll go back to the drawing. See here, 8, we are starting traversing from here, from first index. Is it greater than 32? No. So we'll assign this value to x, and we'll come back that why I need extra variable to track whether the y is found or not. And what we are going to do, I'll just set it to true. Okay, and outside of this I'll just assign the value y to order of that value current, that is this one. Okay, now while we keep going, again we encounter this situation. Now x is already found, we cannot assign that is 24, that will be incorrect. Okay, so in that case we cannot assign that again, that x, but we have to assign the y, because this is the actual smaller value that got swapped with the x. So in this case, second times we find that the array is not sorted, then in the second time only we need to change the value of y, not x. Okay, that's why I took this extra variable. Now we have x and y. What we are going to do, instead of this passing this to array and I, we're just going to say pass x and y. Here we don't need this again, y. Okay, and I'll remove all of this. If root value is equal to x, then we need to give it to value y. Okay, otherwise, else if root value is equal to y, then I'll give it to x. Again we have to put x and y and x and y. Let's run it. Okay, so our sample test cases are running fine, so let's submit it. Okay, now the time complexity of this implementation is order of n. Okay, but what if I tell you that we do not need to perform this in-order traversal to figure out which two values are swapped, this x and y? I mean, we can find x and y directly in the tree when we are performing in-order traversal. Instead of storing values in separate array, we do not need to do that. And this also description, if you go in the end, in the follow-up section, it is saying that the solution using is pretty straightforward. Could you devise a constant on space solution? Okay, here when they are not taking recursion stack space into account. Okay, so without taking that, can we do that? Yeah, of course we can do that. Let's look at the approach. Okay, so since arrays are linear, we traverse linearly. For example, if we are at ith index, we are checking if the I minus 1 at the index, we are comparing these two elements. Okay, so what if we would directly traverse in the binary tree? Okay, in this case these are not linear. In binary tree we are given the node references, that is pointer. Okay, so let's say this is our current root pointer. Okay, so what we're going to do, so this will be our previous, this is our previous pointer. Okay, so the logic will be same, just we applied for this approach, but now instead of checking the values or keeping this simple integer iterator, we are going to use pointer, obviously. Okay, and this x and y will also be pointer, or everything will be same. Okay, so let's simulate this approach. Okay, when our current root is here, okay, our root, let's say root is a pointer. I'm here root, I'm not denoting the root of the tree but a pointer. Okay, and our previous root will pointing here, as here somewhere, let's say this is null pointer. Okay, now when it moves to this, let's say this, then our previous root will be here. Okay, when it moves to this, then our previous root will be this. So it's just following the root. This is our previous root, and will same way, because this we are performing in order, this will be same as like traversing array, but not in a linear fashion. Okay, because this is not a linear data structure. Okay, so now let's implement this approach and see it in action. So I'm gonna remove everything. We don't need this implementation, and I'm gonna declare a few global variables. So first one will be our payroot, that is the pointer which is following our root pointer. Okay, and then x and then y. Okay, another, the same variable we are going to need, boolean, is whether the x is found or not. Okay, and we don't need this one, so I'll just remove it. Any of this one, we don't need it. Okay, I'll just initialize it quickly, that our favorite will be new tree node, that is int minimum. Yeah, why I'm defining this very well, in order to avoid an extra check whether the payroot pointer is null or not. Okay, I'll just show you. I'll come back to this in a second. And x and y is equal to null pointer, and our found x is nothing but false in the beginning. Okay, now here what we are going to do, I'll just remove this portion and we'll check, okay, whether the current root value is less than the payroot value. Okay, the same concept. Instead of our I, we are checking with the pointer. Now this is where beforehand we needed to check whether it is a null pointer or not. Since we already defined with the minimum value a node could have, that is this one, so we do not need to check. If we are not doing this, you can simply add it whether it is okay. So I'll just revert it back. Now again the same condition, if found x, then if not found x, sorry, then we are going to assign x with the previous root, and we'll just change this variable value, it is true, and In the same way, we're going to assign it to root, and the pivot will be our current root. That's it. Okay, now we need to invoke this function that is root, and that's it. Okay, now what we have pointer x that is pointing at one of the nodes, which one is bigger, and a pointer y which is pointing one of the nodes of swapped nodes that is lesser. So now what we have references or pointer to these two nodes. What we have to do, we have to swap these values. Okay, since we have reference, we can easily swap with the x and y that will reflect in the original tree. So what we are going to do, just perform swap operation, simple swap operation, value with the y value. Okay, that's it. Let's run this code. Oh, sorry. Oh, okay, I forgot to remove these things and these variables. We no longer need it. I'll just quickly clean it up. Okay. Oh, okay, all right. So now it should be working. Okay, all right. So our simple test cases are running fine. Let's submit it. Okay, so everything works fine, and obviously for this implementation will be O of 1, but if we are neglecting the recursion stack space, then our space solution will be O of n, otherwise O of n. Okay, thank you guys. I hope you enjoyed this. So please like this video and subscribe to this channel and hit the bell icon and stay tuned.